Bond energies and bond length. We can estimate enthalpy changes of reaction by looking at individual bond energies. We learn to do this in another way by looking at heats of formation or adding up enthalpies of reactions and using a Born-Haber cycle or something like that. So we can also look at bond energies. So we need to define what a bond energy is. Bond energy is the energy required to break 1 mole of the bond in the gas phase. It's always positive, meaning you always require energy to break a chemical bond. They don't just break by themselves. Okay, so bond energies are always positive. And the bond is stronger if it takes more energy to break. Okay, so that should make sense, right? If we look at hydrogen chloride in the gas state, and we break that hydrogen-chlorine bond and end up with a hydrogen atom in the gas state and a chlorine atom in the gas state, the change in enthalpy for that is 431 kilojoules per mole of bonds that are broken. What we see is that compounds that have really strong bonds are more stable and less reactive because they're in a good place. It takes a lot of energy to get them to do something else. A compound with very weak bonds, it's not going to take much to break those bonds and then create new ones. So breaking bonds always requires energy. Bond energies vary from compound to compound. And so what we usually look at is an average bond energy. So it's an average of bond energies for that particular bond, whether it's a carbon-carbon bond or a carbon-hydrogen bond, in a large number of compounds. Because it would just be really, really overwhelming if you had values for each particular compound. The energy does depend slightly on the molecule, and here's an example of that. If we look at breaking a carbon-hydrogen bond in methane, that requires 438 kilojoules. In, I'm blanking, in F3CH, we'll just call it that, it's 446. In Br3CH, it's 402. And in Cl3CH, it's 401 kilojoules. It came back to me now. This is trichloromethane, tribromomethane, and trifluoromethane. I don't know how I lost that, but. So the carbon-hydrogen bond, you might think, well, it's always going to be the same. But it depends on the molecule, because these other atoms that are bonded to the carbon are going to affect various things about that bond. And so instead of worrying about little tiny details, what we do is we take an average. And so the average is 414 kilojoules, and then we can use that in lots of things. Is it going to be exactly correct? No, but it wasn't going to be exactly correct anyway, because everything that's measured has error in it. We see that double and triple bonds have higher bond energies than single bonds do. And that makes sense, because they're sharing more electrons. So we have tables like this. This is an abbreviated one, but we can look in the table if we need to know the average energy of a hydrogen-hydrogen bond. It's 436. An oxygen-oxygen double bond. See here, you look, the single bond between two oxygens, 142, double bond, 498. A lot stronger. If we look, where's nitrogen? Well, here we've got carbon, nitrogen, single, double, and triple bond. The triple bond higher in energy than the double, which is higher than the single.
The CO2 star.
The CO2 star?
Yeah.
So that's coming from this one. The carbon-oxygen double bond is 736 on average, but carbon dioxide, for whatever good reason, I'm sure it has, is significantly higher. And so they kind of bump that out and say, well, But if you're doing CO2, you need to look at this number instead. Good question. So we can estimate, and this is just an estimate, we can estimate the enthalpy change of a reaction using these average bond energies. And so what we do is we look at what bonds are being broken. Breaking is endothermic, positive bond energy. You have to put energy in to break that bond, right? That makes sense. You have to smash it. When bonds form, energy is released. Because law of conservation of mass, if it takes, yeah, that doesn't make any sense. Law of conservation of energy. If you put in energy to break the bond, then when the bond forms, that same amount of energy comes out. So breaking and making, you just change the sign. So bonds forming, exothermic, negative energy. So what we're going to do is we're just going to add up the energy that's needed to break bonds, the energy that's given off when you make bonds, and see what you come up with. So there's different ways to think about it. This is one way. The enthalpy change for the reaction equals the sum of the bonds broken, these are positive numbers, plus the sum of the bonds that are broken. That are formed. That's negative. So you've got bonds breaking, positive, bonds being formed, negative. So they're going to partially cancel each other out. So if we look at this reaction of methane reacting with chlorine gas to form chloromethane and hydrogen chloride, what has to happen in order for these molecules to form? We have to break this chlorine-chlorine bond, and we have to break one of these carbon-hydrogen bonds, right? I have to pull this ball off the model, and I have to pull these two balls apart. And so that's going to require me to put energy in. And you can look those up in the table. And then, now what do we do to get here? Well, I'm going to take one of these chlorines and I'm going to stick it on the carbon. I am making a bond that releases energy. You can look up the value for the carbon-chlorine single bond. And then I'm going to stick this hydrogen on the other chlorine. I'm going to make that bond. And so I write that down as a negative number because it's being released. I add everything up, and I find for this one that the change in energy for the reaction is negative. Okay. We often say that energy is stored in chemical bonds. Why does gasoline provide energy for your car to move? Well, it's got this chemical potential energy. Where is that in the gasoline? It's in the bonds. So when you break a bond, you have to exert energy to break that bond. But an energy-rich compound can undergo a reaction in which weak bonds are broken and strong bonds are formed. And it's always the forming of the bonds that releases the energy. So when a hydrocarbon like gasoline is burned, you're breaking lots of carbon-hydrogen bonds and some carbon-carbon bonds, and those are not super strong bonds. But what you're forming is carbon dioxide and water. Carbon dioxide has two carbon-oxygen double bonds. When those form, they release a lot of energy. And water has two hydrogen-oxygen bonds, and those release energy. And that's where the energy comes from, is we're breaking weak bonds and forming strong bonds. So a potential future fuel is methanol. We know they're already sticking that in the gasoline. No, I'm sorry, they're sticking ethanol in the gasoline. Anyway, never mind. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So I'm going to pause here for a minute. So I cheated and wrote down some of the bond energies from the table, because otherwise it's going to be awkward. Okay, so we need a balanced chemical equation for the combustion of methanol. So CH3OH What is the other reactant in a combustion reaction? Oxygen. And what is formed? Carbon dioxide, CO2, and water. And that's something we should know. Then we need to balance the equation. So on the left side I have one carbon, I've got one carbon on the right, that's okay. Here I've got 4 hydrogens and I've only got 2 over there. So I'm going to put a number 2 in front of the water. And now I've got my carbons and my hydrogens balanced. And over here I've got 2 plus 2, 4 oxygens, and over here I've got 2 plus 1, I've got 3. It's just, fabulous. So this is one of those odd even problems. So let's just double what we've looked at. So I'm going to change this to a 4. I'm going to change this to a 2, and I'm going to change this to a 2. This is the one that we hadn't looked at. We were fixing the oxygens. If I double everything that has carbon and hydrogen in it, then it'll still be balanced. My pointer there, okay, I don't know why it does that. So now I have 4 oxygens here and 4 there, right? Total of 8. And over here I've got 2, and then I can get more in pairs, so I'm going to need 3 over here to get my 8 oxygens on each side. Okay, to use bond energies, we have to look at the bonds that are being broken and the bonds that are being formed. And you can do this in a more thoughtful, shorter way, or you can do it in a longer, less thinking way. What do you prefer? Shorter, more thinking? Okay, so shorter, more thinking is we're only going to look at the bonds that are actually being broken and the ones that are actually being made. The longer way is to say, well, let's just break all the bonds and then let's make all the bonds, and then you don't have to worry about it too much. So over here, methanol, you have to know what bonds you've got going on. So you really need some Lewis structures. And, as long as we're drawing Lewis structures, we should make sure we have our lone pairs. And then oxygen, oh, that's what I forgot when I looked up the table. If somebody has a book, could you look up an oxygen-oxygen double bond? And then over here we've got carbon dioxide. 192? 498. I don't know where I got 192 out of that. Okay, thank you. And here's carbon dioxide. And water. Some of you are really going to hate this. I'm sorry. Okay. So let's look at the methane here. And which of these bonds gets broken? Or maybe, are there any that don't get broken? This oxygen-hydrogen bond. There's an oxygen-hydrogen bond over here, right? So that one stays the same. I'm going to make that one orange because that one's staying the same. Are there any oxygen-oxygen double bonds on this side? No. And there aren't any carbon-hydrogen bonds. And there aren't any carbon-oxygen single bonds. There's only double bonds. So the only one that didn't get broken was this one. And all of these are getting made. So on this example, the thoughtful, shorter approach isn't that much shorter. But we've got 2 of these going on. What's the best way to write this? Well, I think I'll do this for starters. I'll get rid of that. So there are two of these molecules, and for each of them we've got 3 carbon-hydrogen bonds being broken, right? So I've got 3 in this molecule times 2 molecules, so I've got 6 carbon-hydrogen bonds breaking. Does that make sense? And I've got 1 carbon-oxygen bond for each molecule. There's 2 molecules. So 1 carbon-oxygen bond is breaking. And then I've got 3 oxygen molecules. When that breaks, there's 3 oxygen-oxygen double bonds breaking. And then here's the other side. I have 2 carbon dioxide molecules, and I have 2 double bonds between carbon and oxygen for each. So that's 4 carbon-oxygen double bonds being made. And then this one bond here is the guy that didn't get broken over there. So this guy, I overlooked him earlier. He's the same. But I'm making 1 hydrogen-oxygen bond for each of these 4. So that's 4 oxygen-hydrogen bonds. You following me? Right? This gets messy fast. So what I'm going to do is breaking bonds, these are all going to be positive. So I'm going to take 6 times the bond energy for carbon-hydrogen, which I wrote up on the board, is 414. So 6 times 414, and then I've got 2 carbon-oxygen bonds. Those are 360. And then I've got 3 oxygen-oxygen double bonds, and those are 498. This is like the investment. I have to put this money in, and hopefully I'm going to get a payoff, right? So those are all positive, and then the bonds being formed are negative. So minus, and we decided there were 4 carbon-oxygen double bonds, and this is CO2, so we're using the 799, right? Yeah. 799 minus the 4 oxygen-hydrogen bonds, 464, and then we have to add all this up. And this is one of those calculations that you should probably run through more than once because it's so easy to make mistakes. 6 times 414 plus 2 times 360 plus 3 times 498 minus 4 times 799 minus 4 times 464 equals negative 354 kilojoules per mole. You can estimate the energy of a reaction by doing this. And so without going out and messing around with chemicals, you could look at these different things and see, oh, well, this gives me more payoff. Some fuels give you a lot more energy for the amount of carbon dioxide they give off or for the amount of substance that you have to burn. Any questions?
Oh, what would you say? Something about OH not breaking off? Why is it not breaking off?
This didn't break because we look at what we're starting with, and there's already an OH bond here. And the only place that OH bond could go is over here. Right? Ooh. Yeah, see, here's where the thinking involves too much thinking. because there's a problem with this. How many hydrogen-oxygen bonds are there in this two molecules? There's one in each molecule, right? So there's a total of 2 of them over here. But how many are there over here? There's 4 of these. So only 2 of those were pre-existing. So, yeah. So really not such a good idea to do this way. So it's actually minus 6 times 464? Okay, so, we're gonna do this the long way because this is getting messy. So, sorry. So, long way. Let's get rid of that and change that back to blue. So we're going to count all of these because I overlooked something. And so there's 2 of those molecules, and so we've got 2, oh, I'll just leave these blue, 2 OH breaking. And over here, if we're going to count all of those guys, there's 2 each on each of 4 molecules, so there's actually 8 of these. So there's 8, sorry for the mixed up colors. And we've got plus 2 times 464 over here. Except I'm writing 646. You could cancel out and have minus 6 here, but you can see how that can get ugly fast, right? So I did it not quite right. And you just kind of have to know that if the teacher gets it wrong doing the example, that maybe that's not a good sign. So I need to subtract another 2 times 464. And it's actually minus 1282.
So why is the CH bond on the left side 6 and not 12? You're like multiplying by that coefficient.
Because I'm breaking 1, 2, 3 bonds. And I have 2 of these molecules. So 2 times 3 is 6.
So and then you're breaking 1 CO molecule and you multiply by the coefficient.
In this one, each molecule, I'm making 2 bonds. And there's 2 of them. So 2 times 2 is 4.
So even if it's a double bond,
You're only counting a double bond as 1 because when you look up in the table, it lists double bonds and single bonds separately because they have different values. And the second bond is not just double the first one.
okay, thanks.
Good. Anybody else have any questions? You have to look at the Lewis structures because you need to know that this is a double bond and that these are double bonds. Otherwise, it's going to come out wrong.
Can you like put that number in context? Energy is the energy received by the body.
Minus 1282 kilojoules per mole is a fairly high enthalpy of reaction.
What does it mean?
It means that when you burn methanol, it gives off energy, quite a bit of heat to the surroundings. Yeah. So it's negative, it's exothermic. Bond lengths. Average bond length is kind of calculated in the same way. They sort of average them in a large number of compounds. Double bonds are shorter than singles. Triples are shorter than doubles. And so you can look at this table and see that as the bond gets stronger, it gets shorter. Longer bonds generally weaker. There are exceptions. And so here are there's a table of average bond lengths. And that's all very nice.